Now we're going to look at some vocabulary of PDEs. And this is in the text, so one, order of a PDE is the order of the highest partial derivative. And so this could also be mixed partials. Oops, there we go. So if you look at like the heat equation or the wave equation, so we have those. Those are both second order because our highest derivative has two partials there, either xx here or tt or xx there. But you could have something much more complicated with like a ut plus uxt minus uxxx plus uxxt, something like that equals 0. Here we look there and we see that that has 4 derivatives, so this is fourth order. Okay, so that's the order of a PDE. Then we'll talk about number of variables. Okay, so again, this, if we look at either the wave equation or the heat equation, so heat equation or the wave equation, we see 2 independent variables. Okay, those are t and x. And again, typically for these t is time and x is space. This will become more clear as we look at the modeling aspect of these, but right now we're just looking at the vocabulary. So, we could use t's, we could use y's, it doesn't really matter. It's just we see there are 2 independent variables, so we would call this 2 variables. We don't count the dependent variable, the u in this case. So it's a function u of x and t. So it's the number of independent variables making up u. So those are both 2 variables, but suppose we had the heat equation in 2-dimensional space. That would be something like this, and so here we have 3 variables. Because we have t, x, and y. Okay, so next is linearity. Okay, so PDE is linear if the dependent variable and its partial derivatives okay, so we have that they all appear in a linear fashion. Okay, so in other words, not squared, not multiplied together, that sort of thing. Okay, so once again, linear, we've got our heat equation, and we've got our wave equation. Those are both linear. But something that would be nonlinear might be, so nonlinear, you know, that could be something like u sub t equals u sub x squared. If we had more variables, maybe, you know, you might have u sub t equals like u sub xx, u sub yy, you know, something like that. Or, you know, even just say u sub t equals 1 over u sub x. Okay, those are all nonlinear because here, you know, we've got 2 multiplied together. There we've taken a power. Here we've got 1 over. And so none of those would be linear. Now, in particular, we're going to tend to look at we'll look at second order linear PDEs. So a second order and then linear, that could be anything. And now the book uses x's and y's. I'm going to change it to t's and x's. So AUTT plus BUTX plus CXX, UXX. Fix that up there. There we go. Then plus DUT plus EUX plus F times U equals G. And G would be a function of X and T. And so, yeah, A to G may be any functions of X and T. Okay. So we're going to tend to look at these, and I'm going to name that. That's equation 1.1. That's what they name it in the textbook. And so then for equation 1.1, or really any partial differential equation, is homogeneous if G is identically 0. Okay, so it's 0 for all X and T. And you know, we could have something nonlinear on the left-hand side in terms of the U, but as long as we say it equals 0, or you know, has no no function other than things involving U, then we would call it a homogeneous equation. 5, if A to F are constants in equation 1.1, then we say, and we say, say our PDE has constant coefficients. Oops, I think I missed an F there. Constant coefficients. Otherwise, they're variable. We have variable coefficients. Okay. And then finally, 6, we have 3 types of second order linear PDE. Based on A, B, and C in equation 1.1. So in that case, if we call it parabolic, if b squared minus 4ac is equal to 0. Now, if you look at the heat equation, ut equals uxx, then it doesn't really matter whether we call the coefficient here on the uxx either A or C. The way I did it up here in 1.1, way back here, oops, right there, it would be C. But of course, there's nothing that says I could switch the X's and the T's there. But nonetheless, so what we see is that B is equal to 0, A is equal to 0, C is equal to 1. Well, actually minus 1, if I put that on the left-hand side. And so you see we get then B squared minus 4ac is equal to 0. So that would be parabolic. Hyperbolic, if b squared minus 4ac is greater than 0. Well, if you look at the wave equation, okay, in this case we would have A is equal to 1, B is equal to 0, there are no mixed partials in there, and then C is equal to negative 1, because we moved that over to the left side. And so this becomes 0 minus 4 times 1 times negative 1, which is 4, or greater than 0. So the wave equation is a hyperbolic. And then elliptic, again, that would tend to be something like, we'll now change to 2 space variables and write it this way. But we see here then that A would equal 1, B would equal 0, and C would equal 1. And so we get that 0 minus 4 times 1 is negative 4, which is less than 0. And so that's, oops, I guess I didn't write it, elliptic if b squared minus 4ac is less than 0. So those are the 3 basic types of problems, parabolic, hyperbolic, and elliptic. My dissertation work looked at numerical methods for the parabolic and elliptic types of equations. I didn't do anything with the hyperbolic, just the parabolic and elliptic. Okay, and so that's our vocabulary. Again, this is all in the text, but I think it's good to kind of go over it this way, and also to see it with the T's and X's instead of X's and Y's. It's probably nice to see it that way. But yeah, we'll be working with a lot of stuff that looks like this right here. Okay, so we'll call that one done.